Welcome back. We've covered what transformers are and how they work. Today, we're talking about how these massive models are actually trained.
Training a large language model is a massive undertaking that requires careful planning, huge data sets, and enormous computational resources.
Let's start with the data. What exactly are these models trained on?
Modern LLMs are trained on corpus mixtures, carefully balanced combinations of different data sources. This typically includes web pages, books, scientific papers, code repositories, and sometimes conversational data.
The scale is staggering. GPT-3 was trained on about 300 billion tokens. More recent models have been trained on trillions of tokens.
A token is a chunk of text. It could be a word, part of a word, or even a single character. Most tokenization schemes use something called BPE or byte pair encoding.
BPE starts with individual characters and iteratively merges the most common pairs to create a vocabulary of subword units. This balances efficiency with the ability to handle rare words.
Another popular tokenization method is sentence piece, which is particularly good for multilingual models. And there's word piece, which was used in BERT.
The vocabulary size is an important hyperparameter, typically ranging from 32,000 to 100,000 tokens or more. Larger vocabularies can be more efficient but require more memory for the embedding layer.
Once you have your data tokenized, you need to organize it into batches for training. A key metric here is tokens per step, how many tokens the model sees in each training iteration.
Modern LLMs often use batch sizes of several million tokens per step. This requires distributing the computation across many GPUs or TPUs.
Let's talk about the training objective. For decoder only models like GPT, the objective is simple: predict the next token.
This is called a causal language model or next token prediction. Given tokens x1, x2, x3, the model tries to predict x4.
The loss function is cross entropy loss, also called negative log likelihood. It measures how surprised the model is by the actual next token.
Cross entropy is fundamentally about probability distributions. If the model assigns high probability to the correct token, the loss is low. If it assigns low probability, the loss is high.
For encoder models like BERT, the objective is different. They use masked language modeling or MLM.
In MLM, you randomly mask out some percentage of tokens, typically 15%, and train the model to predict what was masked using bidirectional context.
This allows the model to look at both past and future context, which is useful for tasks like classification or understanding, but it means BERT can't directly generate text.
Some models, like T5, use span corruption, where you mask out contiguous spans of tokens and predict them using special sentinel tokens.
Now let's talk about optimization, the algorithm that actually updates the model's parameters to reduce the loss.
The most common optimizer for LLMs is AdNW. It's a variant of the Adam optimizer with better weight decay handling.
Adam adapts the learning rate for each parameter based on the history of gradients. This helps the model train faster and more stably than simple gradient descent.
Weight decay is a form of L2 regulation that prevents the model's parameters from getting too large, which helps with generalization.
The learning rate is crucial. Start too high and training becomes unstable. Start too low and training is very slow.
Most LLM training uses a learning rate schedule with warm up. You start with a very small learning rate, gradually increase it over the first few thousand steps, then decay it over the rest of training.
Common decay schedules include cosine decay, where the learning rate follows a cosine curve down to near zero, or linear decay.
Another important technique is gradient clipping. If gradients become too large, they are scaled down to prevent instability.
Large scale training also uses mixed precision, doing some computations in FP16 or BF16 instead of FP32.
FP16 is 16-bit floating point, FP32 is 32-bit. Using lower precision uses less memory and can be faster, but you need to be careful about numerical stability.
BF16 or bfloat16 has become popular because it has the same range as FP32 but with lower precision. This makes it more stable than FP16 for deep learning.
To save even more memory, we can use gradient checkpointing where we don't store all intermediate activations during the forward pass. Instead, we recompute them as needed during the backward pass. This trades computation for memory, allowing you to train larger models. Training stability is a constant challenge. Large models can experience loss spikes or even diverge if you're not careful.
Techniques like careful initialization, gradient clipping, and layer normalization all help stabilize training.
Layer norm normalizes the activations at each layer to have zero mean and unit variance. This prevents activations from growing too large or too small.
Some models also use auxiliary losses, additional objectives that help stabilize training or encourage certain behaviors.
Now, the amount of compute required for training is measured in FLOPs, floating point operations. Training a large model might require 1023 to 1025 FLOPs.
To put that in perspective, if your GPU can do 100 teraflops per second, you'd still need weeks or months of continuous training on thousands of GPUs.
This is why GPU clusters and specialized hardware like TPUs are essential. Modern training runs use hundreds or thousands of accelerators working in parallel.
We'll dive deeper into distributed training infrastructure in a later episode, but the key idea is splitting the work across many devices.
Another important consideration is data quality. Not all training data is equally valuable.
High quality informative data is much more valuable than repetitive or low quality data. This is why data curation and cleaning are so important.
Deduplication removes near duplicate documents from the training set. This prevents the model from memorizing repeated content and improves generalization.
Training also needs to avoid data contamination, accidentally including test or evaluation data in the training set, which would invalidate benchmarks.
And for safety and privacy, training data undergoes PII scrubbing to remove personal information and safety filters to reduce harmful content.
One interesting phenomenon is that the optimal amount of training depends on model size. This brings us back to scaling laws.
Research from DeepMind on the chinchilla model showed that previous models were undertrained. They should have seen many more tokens for their size.
Chinchilla scaling suggests that for a given compute budget, you should balance model size and data size, training smaller models on more data rather than just making models bigger.
We'll cover scaling laws in more detail in a future episode, but the key insight is that both model size and data size matter for performance.
So, to summarize, training LLMs involves carefully curated datasets with trillions of tokens, sophisticated tokenization schemes, next token or masked language model objectives, optimizers like AdamW with learning rate schedules, mixed precision training, and massive computational resources.
It's a complex orchestration of data engineering, algorithm design, and distributed systems.
Next episode, we're going to talk about transfer learning, the key idea that allows us to reuse these expensive pre trained models for specific tasks.
Thanks for listening. Until next time, keep learning and stay curious about AI.